So, thank you, Chetan. I'm a theoretical physicist, and I don't know much about neuromorphic engineering, but I know a little bit about neural network models as a witness when the initial framework for neural network models was constructed. And so I'm going to tell you a little bit about it. So Chetan asked me to do that, and I agreed. And so I will give a history of neural network long time back. But the basic ideas were essentially associative memory and Boltzmann machines. And they are now recognized as a pioneering contributions to the field, recognized by the Nobel Prize last year. And it's an illustration of how simple ingredients, if you put them in the right manner, can go very far. So let me get started. This abstract I wrote up, and it was put up on some page. I'm not going to read it right now, but I can say that after describing the historical context, I will tell you a little bit about what happens when you try to convert neural network models to quantum framework. And this is some of my own analysis, and it tells you many interesting things, even though you don't know exactly what neural networks are good for. So I start with my connection to this subject. So there was a course called Physics of Computation. It was created and taught by Richard Feynman together with John Hopfield and Carver Mead. And it was just announced with a very vague syllabus, no definite scheme of how the grades will be evaluated. Topics were just off the cuff. Probably the instructors thought of whatever they were dreaming about the previous night. They just landed up there and told us about it. But it had very important insights. And that was an interesting part. I have some scribbled notes from those days, but if I look at it, it doesn't look very comprehensible. So this course was actually taught in first time in 1982, and it was repeated the next year. And it was a very unusual course in the sense that even at Caltech, nobody dared to teach this kind of course again. So what was inside that course? So what Feynman taught in that course is now considered a foundational contribution to the field of quantum technology, and it is very well summarized in the book labeled Feynman Lectures on Computation. Hopfield basically was drafted into this subject. He said many times that I don't know much about it, but he did put some physics into the biological context and constructed a model of associative memory. It was based on what is called the spin glass theory, and I will give you the details of that. And Carver Mead wanted to make neural networks interact with electronics. And he basically took some neurons and made them grow on a silicon chip, and hoping that some connections will develop, and then he will find out how the whole thing works. It was not very successful. But he had to do all kind of interesting things. First of all, the neurons have to remain alive, so he had to feed them with glucose. And the silicon chip will have currents and voltages inside it, and how those things interact with each other. Nobody had a real clue, but since then the technology has progressed quite a lot, and we are able to do much better studies of neurons and what are the kind of electrical signals that propagate inside them. So yeah, this is how I looked like in those days. It's a picture on my what you call graduation day, the day I got my degree, and Feynman was one of my thesis examiners. So let me now get started with the first topic, associative memory. What is the meaning? Well, it's well known in our experience that sometimes we have only some partial idea about some things, and we try to think about this way, that way, etc., and suddenly the full thing crops up in our head. So it's a association where partial data is enough to construct the complete information. The physical model for such a thing is a manifold of data where there are so-called basins of attraction. So the exact information will correspond to a minimum, and all the neighbors around it will correspond to some partial information, and because it's a attractive basin, if you start somewhere nearby, you will roll down to the minimum. So this is the physical picture, and it is good enough. I mean, it will work if you somehow try to figure out some mathematics behind it, and that's what Hopfield did. So what he modeled it on was something which is known as spin glass. These are just models with Ising spins, plus and minus 1, and some couplings between those spins, which I'm calling Wij. So what is observed as the dynamics of neurons are they are generally either in a firing state or a quiescent state, and those two states are mapped onto this plus or minus 1, and the state of the neuron depends on the inputs received by it from all its neighbors through various synapses, and these inputs can be either excitatory or inhibitive. So this Wij are going to represent this connection through synapses, and they will have both positive and negative signs corresponding to excitation or inhibition. So this seems to be a drastic simplification of what a neuron is, but the point is that we are not trying to model a neuron. We are trying to understand the type of behavior which a neuron produces that we will extract or summarize in terms of certain features, and for extraction of those features this model is good enough. And I will come back to this to give some more elaboration. So such a structure of a neuron already existed. It's called a perceptron, and in this binary setting it can be just defined as the state of a neuron, Wij its coupling, that remains how strongly this neuron interacts with its neighbors. There is a bias field which can be called a threshold for firing or remaining quiet, and because it is plus or minus 1, you take the sum over all the inputs, and on which side of the bias it is, just take the sign. So this defines a simple time evolution of this network, where this notation of Ij with these angular brackets represents neuron pairs that are connected by synapses. So such a model was actually known in physics. It's a generalization of what is known as the Sherrington-Kirkpatrick Hamiltonian, and that Hamiltonian is this particular quantity Wij coming for the interaction and BISI for the bias field. So now Hopfield came up with that Bayesian of attraction picture by defining a specific evolution rules of the perceptron. So it is just defined as a sign of this particular quantity in a clever manner, and if the evolution goes from this SI to the sign of this particular quantity, I left out a SI over here, it should have been there in this equation for the Hamiltonian. Then because of this definition of the Hamiltonian, negative side is already there. With this kind of evolution, H is going to monotonically decrease, guaranteed. So if the network is updated, various spins, you go through all of them in some sequence, this is just a perceptron rule, then it will reach the lowest energy state of this Hamiltonian sooner or later. It's a monotonic evolution, and what is known as the spin glasses described by such a Hamiltonian, they generically have a large number of local energy minima, and all these local energy minima then are associated with the various memories which you want to store. So this is one part of the story, the evolution rule, which will construct movement from any point in the Bayesian of attraction towards the minimum. Now the second part is, how do you ensure that the memory which you want to store inside is sitting at the minimum? And that was also available. It's even older than the perceptron story. It's called Hebb's learning rule. And it's very simple. Consider the case where the spin configuration that you want to store is SI bar. And construct these couplings, the synaptic strengths, as this particular quantity. SI bar minus BI is just to offset the bias which is there everywhere. But that's the direct product of SI bar and SJ bar, and the diagonal term is 0. This ensures that if the two spins, SI bar and SJ bar, are the same, the coupling will be strengthened, and if they are opposite, the coupling will become more negative. And this is a simple rule which have put forward, that similar states of the synapses will make that synapse stronger, and if it is inhibitory, then it will make it go in the opposite direction. And that is good enough. So now I will write this Hamiltonian with this Wij. And it is a very simple substitution. I will leave out this bias for the time being to simplify the expression. And you take SI, Sj, and then there are this SI bar, Sj bar, and this becomes a simple contribution of the interaction term. The bias term is inside that constant. And you can immediately see that this quantity is minimum when SI is equal to SI bar, because this thing gets squared and it is equal to 1, and there is a negative sign in front. And there is nothing more you can do to make it more negative. And so you choose this Wij, hold them fixed during the evolution, and then this memory gets stored at the minimum of the Bayesian of attraction. So that's it. That was the end of the story as far as Hopfield models is concerned, but he guaranteed this thing. Now comes the question of what happened when he tried to put it on a computer. Okay? So, well, he did not want to store only one memory, but he wanted to store many memories. So you take the sum of all these different terms of Wij and just average over them. That creates multiple minima, and things will be okay if these various minima are sufficiently far apart in the configuration space. Then they will act as independent memories. But what happens is that is not necessarily always the case, and sometimes these two SI bar configurations kind of overlap, and then there are spurious minima, and then they were called hallucinations of this particular network. We also have hallucinations in our memory where we remember part of one thing and part of another thing and mix it up in some type. So that was not something completely wrong, and Hopfield basically decided to stay with the model. But what limited the performance of the model is this Wij represented all-to-all couplings, because this SI bar was a configuration spread over the whole manifold. Some values of plus or plus 1 and minus 1 over the whole network. And so you have to have a number of couplings which is quadratic in the number of the neural nodes, and when you try to run this algorithm, it becomes impractical to simulate for large number of spins. And Hopfield actually did these simulations on the computers available in those days, and he could do it with about 10, 12 neurons, but that's it. Could not do it much beyond that. But then people actually were able to rigorously demonstrate that the storage capacity with this particular kind of encoding of memory scales as n divided by log n, where n is the number of neurons. So it's proportional to the size of the network. There were some improvements to increase this capacity. In particular, Storkey improved the learning rule systematically, and that could be described by calculating this Wij incrementally. If you have mu minus 1 memories and you want to add one more memory, you add all these kind of combinations of various fields, and this was chosen such that the storage capacity was increased and the overlap between different spin configurations which were stored was reduced. So it certainly did a better job, and it was again analytically rigorous, and it was still restricted that the number of memories stored will be little better than this, but it will still remain proportional to the size of the network. Afterwards, the subject has actually moved much more. People have constructed better networks by introducing essentially non-linearities in the energy landscape. Remember, everything over here was done using quadratic functions, and the minima were defined by calculating essentially gradient, which were linear functions. So by making this whole landscape non-linear, and you can even include multiple layers of these networks, it's a hierarchical structure, and that actually helped to localize the memory stored in the configuration space and increase the capacity. This is an important addition to the mathematical structure, because remember, the configuration space of n spins with values plus or minus 1 has actually 2 to the power n states. And saying that we'll store only order n memories in 2 raised to n states is a terrible waste. But this is where all the games are. People have been able to go beyond the linear case, and they try to get close to this 2 to the power n to a certain extent. But I will leave these models at this particular stage because better things are now available. Okay, so the next topic, that is on Boltzmann machines. This was the second part of the Nobel Prize last year. So neural networks actually minimized the location on the landscape by what is called a gradient descent. What Boltzmann machines do is they do not go to the minimum of the energy landscape, but they construct an annealed Gibbs distribution on this manifold, which can then be sampled. Okay, so the Gibbs distribution will have some temperature, and so it will not have only the minimum, but the other states are also there to contribute to it. Where is this Boltzmann machine definition useful? It is useful in studying what is now called unsupervised learning, where the task is to find the probability distribution of the data obtained in some specific scenario, some experiment, some observations, and then model that distribution to make new predictions. So if you know the distribution, you can calculate the expectation value of some observable, and that can be used somewhere else. So how does it construct a probability distribution? That is the task of the Boltzmann machine. So what is done is the unsupervised learning, they don't know anything about what is the physical context of the data, so they just use some analogies which will guess some initial probability distribution and then evolve it by tuning all kind of parameters to improve the approximation. This is a kind of exercise we do in high school while trying to fit a curve through a data in some sense. But you can't get something from nothing, so you have to make some assumption. I will come back to that assumption. But here you need a criterion for making the probability distribution fit the data as well as possible. There are various methods to compare the two sets of distributions, one an ideal one and the other one is the approximate guess. And the popular way to compare these two distributions is called the KL divergence by the initials of these two people, but information theory, it is generally identified as relative entropy. And it is just a simple expression involving two distributions P and Q. Q is the exact one, P is the approximate one, and you take P times log of P divided by Q, sum over all the states which are there in the data, and by definition of this entropy, or computer scientists call it information, it can be quantified as the amount of information that is lost when Px is used to approximate Q of x. It's a very systematically constructed quantity. It is asymmetric as far as P and Q are concerned, but it has good mathematical properties that it is always non-negative and it will vanish only when P and Q coincide, which will make this log equal to 0. So what is done in the analysis is you parameterize P by some variables and fit the data Qx by minimizing this particular quantity. How you minimize is question of the algorithm. Okay. So as I said, you can't get something out of nothing. So here is the important assumption that Boltzmann machines make, that whatever the probability distribution, it came from some physical process, and the probability distribution is therefore modeled as a Gibbs distribution with some temperature and some Hamiltonian. You are completely free to choose what Hamiltonian you want, and all the parameters which I mentioned in P of x can be also expressed as parameter of the Hamiltonian. That is not a problem. Now it is also possible many times that even though the variables x may be a large set in number, in principle we will observe only a subset of them, and the statistical framework tells you that whatever is not observed is just summed over, is part of the sum over states which is over there, and that produces what is called a reduced probability distribution. And in terms of the neural network models, the unobserved degrees of freedom become what are called the hidden variables. Quite straightforward, there is nothing mysterious about that. And now we go back and stick back our spin class model. Some couplings, some interaction between spins I and j, and some bias. But now the problem is that we are not looking for minimum of this Hamiltonian, but you are looking for some temperature. So you start for some initial state, but evolves toward its thermal equilibrium state. And this is a process again known from a lot of statistical analysis. It's called simulated annealing. And when you do that, you arrive at the distribution P of x. The parameters are tuned to minimize the relative entropy, as I mentioned, and if you get it down as close to 0 as you want, then you have a good model. So this is how Boltzmann machines are designed. But again, the problem comes in that these Wij are too many. It's basically interaction of every spin with every other spin in the network, and if you do that, computational time becomes very large. So these Boltzmann machines are simplified. One structure is called restricted Boltzmann machines, where you break up this network into multiple layers, and connections then exist only between the observed spins and the hidden spins, but there are no connections between the observed spins, and there are no connections between the hidden spins. So these are restricted machines. It turns out that they can do as well as the completely connected Boltzmann machine. There are reasons for that, but let us just take it for the moment granted. And then there are something called deep Boltzmann machines, where there are multiple layers of these hidden variables, one about the other, one after the other. And there is one more quantity which is useful, that this relative entropy is minimized when the two distributions agree. But then you can ask, what is the behavior in the neighborhood of that agreement? So you expand it about the minimum, which will be a quadratic function, and that quadratic function defines what is known as a Fisher information metric, and which satisfies the so-called Kramer-Rao bound. This basically characterizes the best fit that you can obtain from such an exercise, and mathematically it says that there is always a limit to the accuracy you can obtain from this kind of fitting exercise. The Kramer-Rao bound gives that minimum. Okay, so this is a visual pictures which you will have familiarity with. The black dots are the spins representing neurons. The lines are all the connections. One part which is visible, whole other part which is hidden, not visible, and the invisible part is broken up into certain layers. The connections are such that they are going from one layer to the next, but nothing within the layers. And these all are treated in the same statistical mechanics framework constructed by Sherrington and Kirkpatrick. The connectivity is restricted, but the weights which are the connections here, they are still variable. And you can put external bias fields also. But here comes the important point of why such simple-minded structures succeed, because it can be shown based on the Sherrington-Kirkpatrick analysis that they can exhibit regular, periodic, glassy, chaotic behavior. And if these are the patterns which you are looking for in the behavior of the neurons, then this kind of modeling is sufficient. This is a crucial point, that why this structure is taken. It is not because neurons behave like this. It is because what you are looking for in the neuron behavior can be simulated by this particular structure. Okay, so that is as much as I can say about Boltzmann machine. And now let me describe what happens when you try to generalize this to a quantum scenario. And it's a relative question that we don't fully know what are all the capabilities of the neural network. But we are asking a very limited question. If I replace that classical spin network by its quantum version, will I get anything extra? Whether there is some advantage to be added, and it is easily clear that there are limitations. And I'm going to point out those limitations there. But the structure remains the same. Network topology is the same. But now instead of the spins, which are plus or minus 1, we are going to make them quantum bits. And all these inputs which are going into the network and their connections, etc., will be described by some quantum states, whatever they are. So some generalization which is well defined in terms of the Hilbert space structure. I don't have to give the mathematical description of those details. So what happens? And that is well known by the rules of quantum mechanics, that the classical probability distribution allowed you to calculate the expectation value of some observables. O is observable, P is its probability, and you take a whatever weighted average, and that gives you the expectation value, which is what you try to extract from the network. The quantum structure has a generalization, but which is precisely defined, Hermitian matrix, and it has a density matrix rho, which will be the quantum analog of the classical probability distribution, which is much more elaborate, this density matrix. But there are certain things which are known. One is that the density matrix is always positive semi-definite. So if you want to write it down as exponential of some Hermitian Hamiltonian, you can always do it. So you can have a quantum Hamiltonian which will produce this state, no problem. You can also construct the reduced probability distribution by summing over all the hidden variables with the density metric structure. It will give what are called partial trace over hidden variables. No problem with that at all. Even the relative entropy definition generalizes to a similar structure, rho log rho and rho log sigma. There is a difference between the two, and you have to take a trace because it is a matrix. And it has the same properties which was there for the KL divergence also, that it is always non-negative and vanishes only when the two distributions coincide. So you can even construct the Fisher information matrix about the minimum and derive the Kramer-Rao bound, which is corresponding to that, no problem at all. So where is the difference? The difference comes from the fact that this rho and O, which are both Hermitian objects, they may not commute. And this is the only way quantum mechanics can enter this description. All this other stuff goes through without any problem. What caveat that is produced is that if rho and O commute with each other, there will be a basis in which you can simultaneously diagonalize both of them. And then this diagonal form trace rho becomes exactly this, sum over PO. And in this case, there is no quantum advantage. Whatever this rho can do, there will be a corresponding classical version which will produce the same answer. It will look different, but it's not going to give you anything more. And so the non-commutativity is a necessary condition for the quantum Boltzmann machine to offer an advantage. This is a very peculiar fact, but quantum mechanics has to get in somewhere or the other, and the commutator has to appear in some form or the other for the quantum analysis to make a difference. It should be remembered that this condition makes that the advantage depends on the chosen observable, while in the classical case, no matter what observable is there, I have the same prescription. Same probability distribution which I determined, I can calculate any observable. But here it says for some observable there can be an advantage, some observable there is no advantage. It's a problem dependent statement. What next? Well, we can now ask what is the best we can do, and the answer is quite easy to guess. The commutator had to be non-zero, and you get the maximum quantum effect when you maximize the norm of the commutator. Just go to the opposite side. This maximization is possible because rho is bounded. It's a probability distribution generalized to quantum language, but it has still norm less than 1. And the convention of O can be chosen whatever it is, but its norm can be fixed. So this is not going to be uncontrolled expression. And once you maximize the norm, you can quantify what is the Fisher information metric, what is the corresponding Kramer-Rao bound, and all those things now will become dependent on what is observable and what is the state. And it becomes much more clear by giving a simple example. So the example is just 1 qubit. Okay? The density matrix of a 1 qubit can be written as a combination of identity and the Pauli matrices. And this knob being restricted within a unit sphere basically means that R is bounded by 1. So now you can choose an observable, whatever you want, but for a 1 qubit observable, any observable can be written as a Pauli matrix in some direction, and for simplicity let me take that direction to be the z direction. So then I maximize this commutator of rho and O very trivially. If I put O in the z direction, the commutator is large, where rho is essentially some combination of x and y polymatrices, nothing more than that I can do. And it's a degenerate situation because you can take many different combinations of x and y, and all of them will anti-commute with z, but the direction is fixed, and that can be visualized on what is known as a block sphere, the unit sphere with radius equal to 1, that the operator is the z basis, you put the state on the equatorial plane of that particular sphere. And how do you produce this particular state? Well, if you know the direction of the operator, you rotate it by what you call angle pi by 2, and take the state of the quantum network in a transverse direction. And what will it offer? It will give you the best state minimizing this Kramer-Rao bound. And it is best expressed in terms of a sensor problem where you want to observe some particular observable with maximum sensitivity. You construct a probe state rho which is transverse to that particular observable. It's a very simple answer. It's not unknown, rather it has been used quite a lot by astronomers. In lot of observations, they want to detect polarization, which is just a binary observable like a qubit, and what they have to do is they have to adjust that telescope filters on the detectors so that they are all transverse to the direction of polarization they want to measure. Very simple result, but practically useful, and this is how astronomers have been using it. These days there are high precision measurements of polarization of all kind of electromagnetic spectrum as well as gravitational waves, but this is what they have to implement. Answer is very clean. And what I could do is I could minimize this, not minimize, maximize the norm of these two objects in any dimension. One qubit was a simple answer, but a mathematically explicit result can be constructed in any dimension.
But do you have to prepare the state again after each observation? Like, do you have to prepare the state after every observation?
Whichever operator you choose, you have to prepare a corresponding state, because it's a relative statement. If you want to measure a different operator, well, you go and change the state again.
So you can't do partial measurements?
You can't do a global thing where, like the classical physics, once you have probability distribution, you can use it for all observable. That doesn't work. So I will skip the general result. It's not too complicated to work out. But one can take several lessons from this simple result for even a qubit. When is the advantage maximum? When the density matrix is a pure state. That means it is on the surface of the unit sphere and not on the inside. The mixed states often appear where there are hidden degrees of freedom, and they correspond to the interior of the unit sphere, but they will give a commutator norm which is a little bit smaller. And this is not unexpected, because as soon as you insert some environmental effect into a quantum dynamics, you lose some information. So you better have a pure state. but that means that the probe qubit in a pure state is guaranteed to decouple from the hidden degrees of freedom. The hidden degrees of freedom are not going to help you at all for getting quantum advantage. Now you can say that, okay, there are some hidden degrees of freedom I want to keep because it's kind of unavoidable. Even then, there is a powerful theorem called Schmidt decomposition, which says that I can rewrite any quantum state in terms of a product between a visible layer, this I subscript V represents that, and invisible layer I prime with a subscript H over here. And the important point of this Schmidt decomposition is that there is a 1:1 map. For every I, there is a corresponding I prime. And this is the most general state that you can construct, and it tells you that even when you have a visible and hidden degrees of freedom, one layer of hidden degrees of freedom, which is of the same size as the visible layer, is enough to encode all possible quantum correlations. If you add more layers after that, you can get advantage, but that advantage of Boltzmann machine will be classical. It will not have any quantum contribution to it. And this is again a very powerful lesson about how much quantum dynamics can be contributing to whatever can already be done by a classical machine. And this 1:1 map also justifies these restricted Boltzmann machines because it's something in the visible layer and something in the hidden variable, which is what the restricted Boltzmann machine coupling was. Nothing more is needed. So there will be some restricted Boltzmann machine which will encode this Schmidt decomposition structure, and that is enough that it can get the quantum advantage. You don't need a general Boltzmann machine with complicated connectivity. And one mathematical technicality is that because you could maximize this norm of the commutator analytically, in practical calculation, you completely bypass the calculation of the relative entropy. You found the minimum. You don't want to apply a gradient descent to converge to that place in a zigzag manner. You just jump it into one step. And yeah, I already mentioned that for a specific O, you have to find the optimal transverse density matrix, which will offer the best sensitivity as per the Kramer-Rao bound. So this is as much as I have to say about what addition of the quantum dynamics to this Boltzmann machine can do. And I wrote down some more points. They are not related to whatever I talked about, but worth remembering while scanning the literature, that there are other ways people have obtained large quantum advantage, but they kind of bypass the various assumptions which were made in this unsupervised learning model. One construction is actually for the supervised learning model, where there are certain problems with feature map that cannot be easily constructed classically, and if that is the pattern in your data, then a quantum algorithm can help. An explicit example has been constructed, which is based on the discrete logarithm problem. But the question then is the pattern which is there in the data has such a non-trivial structure or not. In most of the analysis of the big data kind of thing, such a pattern doesn't occur very often. The second exception is that the input data of these machines can be the output of a quantum process and not a classical data converted to a quantum language. If that is the case, you can get advantage, and this is because the original data, which is quantum, will have certain kind of coherent correlations which is not present in your classical data. There is a classical analog of this, which is again used by astronomers, that these days they make high resolution measurements which are made not by using one telescope but an array of telescopes. And what they extract from the array of telescopes is both the knowledge of intensity and the phase, relative phase detectors which are separated by some distance. And this intensity and phase in some sense represent analog the quantum variable, where it is a complex number, some magnitude and some angle. And if you have both of them, you can do a lot more rather than having only one of them. And this is what is possible. You have to have a quantum processor, but it should get an input from experiment which is also quantum nature. And if you are able to do that, you can again get an exponential advantage in the analysis. Again, a rigorous result. And the statement which I already made is also well known in a different context, that the optimal quantum state for sensing a signal is an eigenvector of the largest eigenvalue of the quantum Fisher information metric, and it will satisfy the Cramer-Rowe bound. And there is one more fact, which is in some sense a quantum inspired structure, and that has to do with some unusual fact based on Grover's algorithm, that we are dealing with binary variable all the time. But Grover's algorithm actually tells you that a single binary query can distinguish 4 objects. It's a very simple scenario which can be implemented by coherently coupled oscillators. And we have not used that in any of the machine learning analysis. The reason is probably we have not looked in that particular direction. We are stuck with binary variables all the time. But it's possible, and you have to then rely on dynamics of waves. But if we are able to do that, it has a ready-made application, which is analyzing the data in the genome. It's not written in a binary language, written in a language of base 4. And I will stop there. Thank you.